Hi, I'm Herb Gross, and welcome to lecture number 27 in our series Gateways to Algebra, where today we're going to look at multiplying polynomials, and again, hopefully see a very neat connection between multiplying polynomials and multiplying numbers using place value notation. So let's just go and take a look. Remember what we said? We said that a polynomial was a sum of monomials. So once we know how to multiply two monomials, by the distributive property, we'll be able to multiply any two polynomials at all. But let's review briefly what we said, that the coefficient is the adjective and the power of x is the noun. And how do we multiply? We multiply the adjectives, that means we multiply the coefficients, and then we multiply the powers of x. So if I take the monomial 3x to the 5th and multiply it by the monomial negative 4x to the 7th, 3 times negative 4 gives me negative 12. 5 factors of x multiplied by 7 factors of x gives me 12 factors of x. So this would just be negative 12 x to the 12th. Now the question is, suppose I was multiplying two polynomials. For example, 2x squared plus 3x plus 1 would be one of my factors, and suppose x plus 2 was the other one. The thing I want you to notice is, and by the way, whether you remember it or not, and we'll review this later, it's exactly what we did when we multiplied whole numbers using place value, is that what the distributive property says is that each term in the first set of parentheses has to multiply each term in the second set of parentheses. In other words, the 2x squared will have to multiply the x, the 2x squared will have to multiply the 2, the 3x will have to multiply the x, the 3x will have to multiply the 2, the 1 will have to multiply the x, the 1 will have to multiply the 2. And to show you why that's true, I think the easiest way is to show you this in terms of a rectangle. Instead of dealing with 2x squared plus 3x plus 1, let's just call it a plus b plus c. Now, how do you represent a plus b plus c geometrically? As lengths. See, lay off a length a, next to it lay off a length equal to b, next to that lay off a length represented by c, and the total length is going to be what? A plus b plus c. Instead of x plus 2, think of that as being two numbers, d plus e. How do we represent that? A length d followed by a length e. So in other words, a plus b plus c multiplied by d plus e can be viewed geometrically in terms of doing what? Multiplying this length by this length to find the area of this rectangle. But now look what happens over here. If I probably won't draw this too well, but I think you'll get the hang of it. See, if I do this, you see what's going to happen over here? This construction breaks the rectangle down into 6 smaller rectangles, and since the area of the whole rectangle equals the sum of the areas of the constituent parts, look what happens over here. You see, this is a by d, so the area is AD. B by d gives me b times d. This is area c times d. This is what? A times e, b times e, and c times e. Now take a look at what happens here. One way of naming the area of the rectangle is a plus b plus c multiplied by d plus e. The other way is what? AD plus AE plus BD plus BE plus CD plus CE. And you see what's happened here? The AD and AE shows you that what? The A has multiplied both terms in here. The BD plus BE shows you that the B has multiplied each of these two terms. And the CE plus the CD shows you that the C has multiplied each of these two terms. And that, by the way, works in general. In fact, when I went to high school, they taught me that when you multiplied the sum of two terms by the sum of two terms, they taught me this magic thing called the rule of FOIL, which I memorized and never fully understood. See, FOIL is an acronym. That means it's an abbreviation that it stands for something. F stands for first, O stands for outer, I stands for inner, and L stands for last. And what we were told was, the rule of FOIL said what? Multiply the two first terms in the parentheses. See the first one here and the first one here. Then multiply the two outer terms, two outside ones. See, these are the two outside ones. Now the two inside ones, and now the two last ones. Well, this is the last one here. This is the last one here. Okay? And that works. But notice what that's a special case of. When you get all through here, didn't the A multiply both the C and the D? And didn't the B multiply both the C and the D? So the rule of FOIL is simply an abbreviation for a very, very special case. But the general case is what? Every single term in the first set of parentheses has to multiply every single term in the second set of parentheses. There's nothing wrong with memorizing shortcuts. The danger is if that's the only way you know the result. In other words, if there's logic involved, that's a very bad way to do things because you can memorize and not understand. See, sometimes it's fine to memorize. You know, to this day, I think it was about the 4th grade that I learned the name of the 5 Great Lakes. And whenever there's a crossword puzzle, I always get them right now. And the reason was, I don't know if you learned it this way, they taught us the word Holmes, H-O-M-E-S. See, that was the geography teacher's rule of foil. H stands for Huron, O for Ontario, M for Michigan, E for Erie, and S for Superior. So by memorizing the word Holmes, I know the names of the 5 Great Lakes. Well, I never use them in any logical situation, so it doesn't really matter if that's the only way I learn them. If somebody says, name the Great Lakes, I can't just rattle them off. I have to think of what? Holmes, H-O-M-E-S. You see what I'm driving at? But the important thing is, when it's a logical situation, memory is okay for a shortcut, but make sure you can derive it in case your memory fails you. But let's go on and let's do a typical problem just to make sure we understand this. Let's suppose the problem was one polynomial is going to be 2x squared plus 3x plus 1. And the other polynomial is going to be x plus 2. We don't want to take anything too complicated right now. We'll save those for the study guides because all we want to do here is to make sure you get the idea. What was the rule? The rule said every term in the first set of parentheses has to multiply every term in the second set of parentheses. So let's start with the first term over here. It has to multiply what? Both the x and the 2. So the 2x squared multiplies the x. That's going to give you 2x to the 3rd power, right? Because x squared times x to the 1 is x to the 3rd. The 2x squared also has to multiply the 2. The 2 times the 2 gives me 4. That's 4x squared. Now the 3x has to multiply each of the terms here. So the 3x has to multiply the x. That gives me 3x squared. The 3x also has to multiply the 2. That gives me 6x. Then the 1 has to multiply both the x and the 2. So 1 times x is x. 1 times 2 is 2. Now what do I have for an answer so far? 2x to the 3rd plus 4x squared plus 3x squared plus 6x plus x plus 2. But we already know from adding polynomials that we can combine like terms. So we have the 2x to the 3rd power. Then 4x squared plus 3x squared is going to be what? 7x squared. 6x plus 1 is the same as 6x plus 1x. That's 7x. And then the 2 over here. So what is this product? 2x squared plus 3x plus 1 times x plus 2 is 2x to the 3rd plus 7x squared plus 7x plus 2. Now, did you notice what we did here? I want to show you that this is word for word exactly the same thing that we did, okay, when we learnt how to multiply in arithmetic. Let's look at 231 times 12. To give you a preview of why I'm doing that, see, look at the coding over here. This is what? 2x squared plus 3x plus 1. There's a 2 in the x squared's place, a 3 in the x place, and a 1 in the 1's place. Here there would be what? A 1 in the x place and a 2 in the 1's place. In other words, I'm going to do this problem as if this was 1s, 10s, 100s, but I'm also going to show you this is the same thing if this was 1s, x's, and x squareds. Let's just do this problem the traditional way. Didn't you say 2 times 1 is 2, 2 times 3 is 6, 2 times 2 is 4. Then you said 1 times 1 is 1, 1 times 3 is 3, 1 times 2 is 2. Did you notice that every single digit in the bottom number multiplied every single digit in the top number before you were done? Then you added these up, and you get for your answer what? 2,772. Let me review for you the adjective and noun format over here. See, for example, when you said that 2 times 3 was 6, why did you put the 6 over here? Well, the reason was the 2 is modifying 1s, the 3 is modifying 10s. When you multiply the 2 adjectives, that gives you 2 times 3 is 6. The 2 nouns are what? 1s and 10s. 1 times 10 is 10, so the 6 went into the 10s place. Why did the 4 over here go into the 100s place? Because the 2 times 2 is 4, but what were the nouns? 1 and 100. 1 times 100 is 100, and therefore the 4 went into the 100s place. For example, when you said 1 times 3 is 3 here, why did the 3 go in the 100s column? Because the 1 is in the 10s place, the 3 is in the 10s place, and 10 times 10 is 100. You see, when you kept indenting over here and shifting over, every time you indented, you were multiplying by 10, by the next factor. Anyway, we then added these up, and this was the right answer. Now, let's copy this exact same thing over again, but instead of calling these 1s 10 to the 1 power, 10 to the 2nd power, and 10 to the 3rd power, let's copy this over, but now it's going to be 1s, x's, x squareds, and x to the 3rd. And watch how neat this is. You see, if I cover up that top, doesn't this look exactly like what we did before? But you see what's happening now? Is 2 times 1, 2. Yes, but what's the noun? These are both in the 1's place, so the 2 goes into the 1's place. Is 2 times 3, 6? Yes, but what's the noun? The 2 is in the 1's place, the 3 is in the x place, 1 times x is x, so the 6 goes into the x place. Okay? 2 times 2 is 4. What column does it go into? 1 times x squared is x squared, so the 4 goes into the x squareds column. 1 times 1 is 1, but it's what? An x times 1 is x, so the 1 goes in the x column. 1 times 3 is 3, but the nouns are what? X here, that's x squared, so the 3 goes into the x squared column. 1 times 2 is 2, but what are the nouns? The 1 is in the x column, the 2 is in the x squared column. X squared times x is x to the 3rd power, so the 2 goes into the x to the 3rd power column. And you see what's happened over here? I don't know if the picture's wide enough to get most of this. Let me see if I can jiggle some. It doesn't really matter if we can do it or not. What I did want you to get to see was that if I leave the labels out, this picture here looks exactly like this picture over here. They're exactly the same thing. And all we've shown is what? That this not only says that 231 times 12 is 2,772, it also says what? That 2x squared plus 3x plus 1 multiplied by x plus 2 will always be what? The single polynomial 2x to the 3rd power plus 7x squared plus 7x plus 2. And in fact, the arithmetic problem is the special case where we take x to be 10. And let's just do another one just to make sure that you have the hang of this thing. Suppose I say, let's multiply 5x squared plus 2 by x cubed plus 4, x to the 3rd power plus 4. What's the rule again? Very simple. Every term in the first set of parentheses is going to multiply every term in the second set of parentheses. So the 5x squared has to multiply the x cubed, and it also has to multiply the 4. And the 2 also has to multiply what? The x cubed and the 4. So now I just use the monomial rule. See, the 5x squared times 5x to the 3rd. Remember, whenever any number is missing, if it's a coefficient, we can assume that it's 1. If it's a power of x that's missing, like with a 4, we can always assume it's the 0's power. So you can even do it that way. You can say 5 times 1 is 5. X squared times x to the 3rd is x to the 5th. 5 times 4 is 20. X squared times x to the 0 is x to the 2 plus 0, or x squared power. So that's 20x squared. Then this is going to be what? 2x to the 3rd, and 2 times 4 is 8. So the answer to this problem is what? Simply 5x to the 5th. Oh, I see. The only reason I changed here is what did we agree to do? We simply agreed to list the terms in decreasing order. In other words, 5, 2, 3, 8 is out of order. It should be what? The highest power is the 5, then write the 3 next, then the 2 next, and then the degree 0 term, the constant. So the official way of writing this is what? 5x to the 5th plus 2x to the 3rd plus 20x squared plus 8. By the way, one quick way of checking this, it's not 100%, but a quick way to check this is if this product is always going to equal this should be true no matter what x is. Well, a very easy number to pick is x to be 1, because that's easy to work with. See, if x is 1, this is just 5 plus 2, which is 7, and this is just 1 plus 4, which is 5. So when x is 1, this is 7 times 5, or 35. When x is 1, this is just what? 5 plus 2 plus 20 plus 8. So 5 plus 2 plus 20 plus 8. That also comes out to be 35. That doesn't prove that this is correct, but it does prove what? That at least when x equals 1, this checks. See, a lot of times if something is wrong, if you just quickly check it by putting in one particular number, it'll turn out to be wrong in that case. But if you want a quick check rather than going through the whole thing, this is the way you do it. Now, I'm going to show you how to do this by place value. See, suppose I wanted to do this by place value. What's the multiplier of x to the 3rd? Isn't that a 1? Okay, is there any x squared term in here? No. Is there any x term in here? No. Is there a constant term? Yes. So in other words, in terms of the language of place value, x to the third plus 4 would be written as what? 1, 0, 0, 4. How would this number be written? It's a 5 in the x squared place. There are no x's, so that means there's a 0 there. And there are 2 1s, so that means there's a 2 here. So in other words, in the language of place value, this messy problem can be rewritten the same as if it were just this. Now, how do we multiply in regular arithmetic? Every digit in the bottom number multiplied every digit in the top number. The only difference is going to be when we're working with x rather than 10, is that we can't carry because we don't know what the trade value is. But look at this. Doesn't it say 2 times 4 is 8? 2 times 0 is 0. 2 times 0 is 0. 2 times 1 is 2. 0 times 4 is 0. 0 times 0 is 0. 0 times 0 is 0. 0 times 1 is still 0. I'm doing this for the dramatic effect of showing you that every single digit in the downstairs number is multiplying every single digit in the top number. 5 times 4 is 20. 5 times 0 is 0. 5 times 0 is 0. 5 times 1 is 5. So now I add up. There's what? 8, 0, 20, 2, 0, and 5. So what's the answer? 5x to the fifth plus 2x to the third plus 20x squared plus 8. And what was the answer that we got before? 5x to the fifth plus 2x to the third plus 20x squared plus 8. By the way, if you do want to see this more clearly, in order not to lose sight of the fact that the 20 is in the x squared place, what you might want to do is do the problem this way, meaning before you even start this problem, put in all of the column values. And see, that way you see that the way you're going to read this is what? 5x to the fifth, there are no x to the fourth, there's 2x to the third, there's 20x squareds, no x's, and 8 1s, okay? And by the way, if you have more than 2 factors, you just do them 2 at a time. See, suppose somebody says to me, multiply x squared plus 1 by 3x plus 2 by x to the third plus 4. Suppose they give me something like that. Well, what did you do in regular multiplication when somebody said multiply 3 numbers? Didn't you just multiply the first 2? You said 2 times 3 was 6. 6 times 4 is 24. Or you could have said what? 3 times 4 is 12, times 2 is 24. In other words, you group these and never had to worry about multiplying more than 2 numbers at a time. We're going to do the same thing over here. I can group these like this. Don't I already know that the product of 2 polynomials is a polynomial? Let's see if we can't do this a little bit faster now. I want the x squared to multiply each of these terms. When x squared multiplies 3x, it's just going to increase each exponent by 2. So this will become what? 3x to the third. X squared times 2 will be 2x squared. Then the 1 multiplies the 3x to give me 3x. Then the 1 multiplies the 2 to give me 2. So the bracketed expression is just what? 3x to the third plus 2x squared plus 3x plus 2. What am I now going to multiply this by? X to the third plus 4. Isn't this still this is now what? Excuse me. This is now what? 1 polynomial. And I'm multiplying it by another polynomial. What's going to happen now? Every single term in the first set of parentheses is going to multiply every term in the second set of parentheses. So the 3x to the third has to multiply both the x to the third, right, and the 4. The 2x squared has to multiply both the x to the third and the 4, okay? The 3x has to multiply both the x to the third and the 4, and the 2 has to multiply both the x to the third and the 4. And now what do I have over here? A sum. Each sum is what? The product of 2 monomials. I know how to handle that, so I just combine what I see over here. This is going to give me what? 3x to the third times x to the third is 3x to the sixth. 3 times 4 is 12, 12x to the third. X squared times x to the third is x to the fifth, and there's a 2 over here. The 2 times 4 gives me 8x squared. 3x times x to the third gives me 3x to the fourth. 3x times 4 gives me 12x. 2x to the third, of course, is 2x to the third, and 2 times 4 is 8. Now I can go looking to combine like term. There's an x to the sixth term over here. That's 6x to the sixth. There's 1x to the fifth term over here. That's 2x to the fifth. How many x to the fourth terms do I have? Just 1. That's 3x to the fourth. How many x to the third terms do I have? I have 1 here and 1 here. 12 and 2 is 14. That gives me 14x to the third. Now what am I looking for? X squared terms. There's 1 here, and I guess that's all. How many x terms do I have? There's 1 over here. That's 12x. How many constant terms do I have? That's this. So when I multiply these three polynomials together, what one polynomial do I get? 3x to the 6th plus 2x to the 5th plus 3x to the 4th plus 14x to the 3rd plus 8x squared plus 12x plus 8. By the way, suppose I wanted to do this in coded form, in other words, in place value form. X squared plus 1 would be 1, 0, 1. You see why? 1x squared, no x's, and a 1. 3x plus 2 would be 3 x's and 2 1s. And x to the 3rd plus 4 would be 1 in the x third place, none in the x squareds, no x's, and 4 1s. So the problem would look something like this. I would first multiply 101 by 32, namely 32, and whatever that answer was, I would multiply that by 1004. So let's just look to see what that looks like. Look how neat this comes out in the sense that you're not blinded by all the different nouns now. They're all being tabulated down here. See, 2 times 1 is 2, 2 times 0 is 0, 2 times 1 is 2. 3 times 1 is 3, 3 times 0 is 0, 3 times 1 is 3. So I now add these up. That gives me what? 2, 3, 2, 3. Now I'm going to multiply that by what? 1, 0, 0, 4. This gives me what? 4 times 2 is 8, 4 times 3 is 12, 4 times 2 is 8, 4 times 3 is 12. Then I'm going to get what? 2 0 rows. Then 1 times 2 is 2. You don't need these zeros in here. All you have to make sure is what? That the first time you multiply by this, the first entry comes under what you're multiplying by, and putting these zeros in takes care of that for you. But you don't have to know that. See, 1 times 2 is 2, 1 times 3 is 3, 1 times 2 is 2, 1 times 3 is 3. Now I can add these up, and what do I get? 8, 12, 8, 14, 3, 2, 3. And how do I now read this answer? 3x to the 6th plus 2x to the 5th plus 3x to the 4th plus 14x to the 3rd plus 8x squared plus 12x plus 8 1s. And you see how this goes? We'll come back and do one more problem before we stop for this particular lecture. But keep in mind right now, the same as everything else, I want to make sure you understand the mechanics before I give you any kind of practical applications with this. It's sort of like saying first you learn the multiplication tables. See, first you learn that 3 times 9 is 27. Then you learn how to solve a question like, at $3 each, how much do 9 handkerchiefs cost? See, learn the arithmetic first, then we'll learn where you use it. But I want you to become skilled with the computational part first. By the way, I should point out, now that we know how to add, subtract, and multiply, that in many problems, aren't you going to have multiplication, addition, and subtraction all combined? Sure you are. So let me just close today's lesson with just one more illustration. Here's a real neat, messy one for you. Look what this says. You have a 2, then braces, then a 5x squared, then brackets, then a 6, then parentheses, 2x plus 3, close the parentheses, add 4, close the brackets, and then you add 2x to the 3rd, and then you close the braces. Now, here's the thing. Has anything changed since the course began? What was always the rule for removing parentheses? Didn't you always start with the innermost set of parentheses and work your way out? See, where is the innermost set of parentheses? Isn't it right here? So the first thing you're going to do is what? Multiply the parentheses by 6. The 6 multiplies the 2x, that gives you 12x. The 6 also multiplies the 3, that gives you 18. So this gets replaced by 12x plus 18. But you're still in the bracket, so you still have to do what? Add the 4. But the 18 and the 4 combine to give you 22. So the bracketed expression is now simply what? 12x plus 22. Remember, of course, you can't combine the 12 and the 22 because the 12 is modifying x's, but the 22 isn't. Now what's happening to the brackets? Multiplication takes place before addition, so the brackets have to get multiplied by 5x squared. So each term inside the brackets has to get multiplied by 5x squared. The 5x squared multiplies the 12x. Same rule again. Multiply the coefficients, multiply the powers. Adjectives, nouns. 5 times 12 is 60. X squared times x. That's 2 factors of x and 1 more factor of x is 3 factors of x. 5 times 22 is 110. 110 what? X squared. And now you're still inside the braces, so what happens next? The 2x to the 3rd power gets added on. Now let's look inside the braces. Can we combine anything? Well, here's an x to the 3rd term, here's an x to the 3rd term. 60 plus 2 is 62 whenever 60 and 2 modify the same noun. So this becomes what? 62x to the third, and we still have what? The 110x squared inside the braces. And what happens next? The braces are being multiplied by 2. So the 62x to the third becomes 124x to the third. The 110x squared becomes 220x squared, and therefore this whole mess over here simplifies into what? 124x to the third power plus 220x squared. In other words, what this might say in terms of a program is input x, multiplied by 124, add 220, multiplied by x, and multiplied by x again. See, and that's a much less complicated program than trying to talk about this. But what I'd like you to do is when I finish this lecture, is for you to make sure you can look at each of these steps and see how what we've been doing gradually has been building from day one to where we are right now. In other words, as we learn new material, we're taking for granted that what? All the things that we learned in the past are still true. And that's why mathematics sometimes is very difficult for students, among other reasons. And that is, you can't hope that something's going to go away. See, if you're studying literature and you don't like French literature, when you get to the chapter on Spanish literature, maybe you won't hear anything more about French literature. You see? If you don't like Western civilization, wait till you get to Eastern civilization. But in math, you can't do that. As we get to polynomials, has all the stuff that's happened before still remain valid? And we have to remember that all those rules that we learned before, even though we haven't talked about them for a long time, they are still in effect. And so hopefully you're beginning to see how polynomial arithmetic is just one more step that we've added on to the string of things we've been doing in the game of algebra so far. But I see by the clock on the wall that it's about time to pack it up for this particular lecture. So again, let me say to you, study hard, have fun, stay young. See you soon.